Today we have a webinar number 10 already with Professor Isabel Marrucho from Instituto Superior Técnico Universidade de Lisboa, if I pronounce it correctly. Professor Isabel Marrucho is indeed a full professor at the Chemical Engineering Department, and currently she is a vice president of the department and the coordinator of the Master in Chemistry. Her research is carried out at Centro de Química Estructural, where she is the coordinator of the thematic line SUSCHEM, Sustainable Chemistry for Environment, Energy and Manufacturing, covering a wide range of research activity between thermodynamics and physical chemistry, supramolecular chemistry, and separation processes, showing the ability of ionic liquid and deep eutectic solvents in applications such as isotope breaking, energy field, biohydrogen production, carbon capture, extraction of micropollutant for water, and so on. Dr. Isabel Marrucho has published over 250 papers in international peer-reviewed journals with more than 18,000 citations. So it's a great honor for us, for the EMIL community, to have a Professor Isabel Marrucho here with us today. So Professor Isabel, the stage is yours.
Thank you so much. Thank you so much for your introduction. And hello, everybody. Good afternoon for Europe. Good morning, I think, for America, wherever you are. It is a great honor to be here. It was in fact a pity that we didn't get to go to Chile last year, but I have to congratulate the organizing committee of EMIL for this great idea of the webinars. It's truly a very nice way to connect the community. If somebody had questions about if this community is alive, I can look at here, and we have so many participants that yes, we are alive, and there are many new members in the community, which is very good. So I come from IST Técnico, and although I like very much this picture, Técnico is not all this picture. Técnico is the school here on top of the hill, and the rest is Alameda in Lisbon. And the chemical engineering department is this tower, the South Tower. Our lab is on the 11th floor of this tower. And so we have a very nice view of the old city, the downtown, and the Tagus River. So Técnico is the biggest engineering school in Portugal. We have around 11,000 students and around 1,000 of faculty members. This is my group. Before the pandemic, nobody is wearing masks, as you can see. So we are here at the entrance of the South Tower, the Chemical Engineering Tower. And I thanked the organizing committee, and now I have to thank my group for all the good work that they have been doing. Which led to this communication and led to the variety of subjects that we deal with. Thank you so much for everybody that belongs to this group, or whoever belongs to this group. Okay. So let me just close here all the windows. Okay. So polyionic liquid. So this is a EMIL seminar. Typically, the people have been presenting on eutectic solvents and ionic liquids, and today I'm going to talk a little bit about polyionic liquids. Polyionic liquids are a subclass of polyelectrolytes that have ionic liquid moieties in the monomeric units. And these monomeric units, of course, are connected through a polymeric backbone. Polymeric ionic liquids share the same properties of ionic liquids. So they are designer polymers. They have a high ionic content. They have Coulombic forces. And so they keep the affinity properties of ionic liquids. which is very important for the applications that we do in my group, because we are based on affinity. We based our separations on affinity. However, polymeric ionic liquids have a main advantage compared to ionic liquids, which is the mechanical stability and the improved processability. And so they are functional materials that combine the properties of ionic liquids with those of polymers. So we can have polycations if we polymerize the cations. So if the cations have the double bond, polyanions if we polymerize the anions, or polydesviter if we polymerize either the cations or the anions. Typically in my group, we work with polycations, especially because they are easy to synthesize, and also because we've realized that the anion plays a predominant role in affinity separations. And so we want the cation to be free and to interact with the solute that we want to extract. In terms of applications of the polyionic liquids, of course, that they are very much used in energy as solid electrolytes and also as membranes, battery membranes. They can also be used as sensors, as in catalysis, and many other applications that you can see here. Today, I'm going to talk specifically about two applications that we work in our group. One of them is in analytical chemistry and involves solid phase microextraction. I think that a little bit has been said about polymeric ionic liquids in solid phase microextraction. And the other is on gas separation membranes. So starting with SPME, SPME is a very attractive concentration and sample preparation technique, since it's solventless and it is quite easy to use. It's non-destructive and it's non-invasive also. It has been greatly used in the food industry, for example, to test on pollutants like pesticides and pharmaceuticals. It has been used in the determination of purity in the chemical industry, in the study of animal wildlife, and also in the medical field. I am sure that all of you know that the breath analysis is becoming a powerful tool of identification of disease, and SPME can greatly leverage the power of the breath analysis. For instance, it's now known that the acetone is an indication that you have diabetes, or nitric oxide is an indication that you have asthma. So how does it work? In fact, we have here a fiber, and this fiber is protected by a needle that is acted by this plunger. So here I have the fiber that is coated on a silica support and is protected by the metallic protection, the needle. So when I want to use it, what I do is I insert the needle in the sample, and I sample the head space of this flask, so it's non-invasive, non-destructive. Here I have my fiber, and it's sorbing the compounds. I take the needle out and I desorb the compounds in the GC inlet, and I analyze all these compounds. Of course, that this is a commercial technique, yet there are many fibers that can be used for this purpose. Typically, there are only three polymers that can be used for this application. PDMS, polydimethylsiloxane, polyacrylate, and polydivinylbenzene. One can wonder, is an application as good as this one, as widely used as this one, only three polymers are typically used. If we take a look at the Supelco catalog, which is the brand that supplies these fibers, we can see that they have fibers that are produced by polymers. They are made of polymers only. And there are others that have carbons in them, carboxane. And so this means that we have fibers that do only absorption of the compounds. And there are fibers that just by having carbons inside, they do absorption and adsorption. So they have a dual mode of absorbing the compounds. And there are basic differences between these two types of fibers. Although the fibers that are non-porous, so only made of polymers, they have a higher capacity, they have a small surface area. And thus, it takes a long time for the uptake of the compounds, and it also takes a longer time to release the compounds and recover the fiber. And there are some times where we need to have higher surface area. We need the sample to sorb and desorb quickly and not take the duration of hours, for example. And so this is our idea to start playing around with the fibers. So all the work that I'm going to show here on SPME was done by David Patinha, which was a PhD student in my group. And now it's a process chemist in Scion, which is a company that deals with chromatography. So his skill was greatly, they really take advantage of his skill, of the skills that he learned during his PhD. And as David said, we prepared 4 types of fibers: the thick, the thin, and the thick and the thin are dense, and the particles and the porous are fibers that have an enhanced surface area. So let's quickly go through these types of fibers and what they do and what David did. So David took advantage of the work that we were doing in gas separation membranes, and he used the polydiallyl alkyl methyl ammonium, TFSI, with several alkyl chains. Oops. Okay. With several alkyl chains. So the way that he did it was we had a mold, and we filled the mold with the solution with the polymer. We put just a handle, and then we took it to the UV curator. In the end, we just dropped this mold, which was made of glass, in an HF bath to dissolve the mold. And here we have our fiber. So it was quite simple to prepare. However, it did not allow the flexibility to play around with the size of the thickness of the coating. So we prepared 3 fibers with each one of these polymers that we have here. And we can see here that the fibers were 67 micrometers thick. So let me show you what we did with these fibers. This was David's first work. And we compared, we used several compounds that you can see here, maybe polar compounds. And the total peak areas are larger for this polymer that has a chain length of 14 than for the other fibers that we prepared, including the commercial fiber. Here we can also see that for alcohols that had longer alkyl chains, the fiber with the C14 did a much better job than the others, and a much better job than the polyacrylic acid fiber, commercial. This work was done on spiked urine so that we had the matrix effect and we could see the recovery. The recovery ranged from 60 to 104, and repeatability was quite good, between 6 and 17, taking into account that this was his first work. However, what he noticed is that it was too thick, and the materials that were sorbed inside, it took a long time for them to desorb and to recover them. And so the idea in the next work was to develop what he called the thin fiber. And so for the thin fiber, we had the collaboration with an Indian group that synthesized the polymer for us. And this is a copolymer, as you can see. So we have in one of the monomers is an ionic liquid and the other is not. And we are going again to play with this side chain. It can be an alkyl chain, a benzene group, or an ethyl group. We did the coating using an airbrush, so an airspray, and we put our wire on a motor, always rotating while we coated the wire in a hot chamber. So with this, we got a coating that was very thin, between 8 and 10 micron. And let's see if it enabled us to completely desorb our sample from the fiber. So here we have the 3 polymers mentioned before. And what we did this time, it was soil. And we used the well-known mixture Betex, benzene toluene, ethylbenzene, and xylene to test the fiber. And as you can see here, we could get some selectivity. So we could extract very well the ethylbenzene with the fiber that had a long chain, and in particular side chain. And in particular, this was a very nice fiber for all the other compounds. Realize that this time the commercial fiber was PDMS, and it is here. So we are doing much better than the commercial fiber. Repetitivity here is quite good. However, however, in the thin fiber, what we realize is that it was very thin. And so we would like it to have a high surface area so that we don't have to expose our fiber for a long period of time to the sample. And so we went back to those polymers that we have worked in the thick and the thin fibers. And David had always these great ideas. And he just came up with this idea that it was very simple just to grind the polymers and use silicone to coat our fibers. And this was a very interesting work because it was very simple. So the particles had a size between 2 and 10 micra, and you can see here the wire before coating and the wire after coating. You can see that the increase was in 46 micra, which divided by 2 is around 20 micra. But here we have the surface area effect. Okay. Okay, so we used the complex sample to compare this particle coating fiber. First one with alcohols, and here we can see that we have an effect of the anion. So when we have polar compounds, it's the polymeric ionic liquid with the bromide counter anion that works really well. And here we have the 2 commercial fibers, the polyacrylic acid and polydimethylsiloxane. And we also did silicone just to make sure that silicone did not absorb. However, when we tested our fiber in the Betex mixture, what we got is that the best fiber was the one that had the TFSI anion. And the TFSI with the benzene substitution group. So we can see here that our fibers are much more, have a higher extraction efficiency than the commercial fibers, that we have selectivity through the designing of specific interactions. So here in the case of the Betex, the pi-pi interactions, and here through hydrogen bond basicity. And because we have a very large surface area. The bad thing or the problem about these fibers was really the repetitivity, because as you can imagine, each time we use the fiber, we would lose some of the particles, and that would affect the performance of the fiber. So here only stable over 50 injections, we could not go anymore. Here I also wanted to show very quickly a study that we did to see if we could distinguish smokers from non-smokers. So we went around our research institute collecting urine samples from smokers and non-smokers. And in the end, we analyzed them for benzene and toluene. And it was quite interesting to see here we use the commercial fiber DVB CAR PDMS. So it's a fiber that is carboxane. And it is very interesting to see that we have, at least for toluene, a much better detection limit than the commercial fibers. And it's also interesting to see that we can distinguish smokers from non-smokers. So this was just for fun. We did it just for fun to see how bad or how good were these fibers with the particle size. Then we evolved to the porosity, the porous coatings. This work was done together with Ionic in the University of Stockholm in Sweden. So here what we did to create porosity, we really wanted to create porosity. And so we used a mixture of our polymeric ionic liquid, which is this one here. So it's an hydrophobic, it's a TFSI with TFSI contranion with polyacrylic acid. So we made, first we hatched the wire. We hatched the wire, then we dipped it in the solution. So it was a 1-to-1 in weight solution. And then we put this inside of an aqueous solution of ammonia. And what happened was that in situ complexation of the polyacrylic acid occurred since it was, it deprotonates. And so it binds and it binds to the pill and it forms a network. And then we have a phase separation in the aqueous environment since the TFSI is not soluble in water. So let me show you here some of the details. So here it's the fiber after coating. After 1 hour of immersion, nothing happened. We can see that it's starting to scratch there, but still porous is not, it's not good enough. And then after 4 hours, we have this fiber here that, yes, it is porous. And here you can see that it is 20 micra of thickness. This fiber is around 200 micra. And you can see here what I was talking about, the deprotonation of the carboxylic acid of the polyacrylic acid. So let's see how this fiber performs. So we had great hopes on this fiber. So we tested a very wide sample of compounds, and this is the results that we got. First of all, realize the difference that it is between having a porous fiber and a non-porous fiber. So it's the red and the green. So the red is, the peak areas are much higher. It has a much higher sensitivity than the green. Then realize the comparison of our porous with the DVB carboxane PDMS. Again, we have the peak areas are much higher for this fiber that we prepared with porosity and with very, it's not very thick, it's 20 micro thick. And it can really sorb the analytes that have a higher vapor pressure. So analytes that do not have a very high vapor pressure, the heavier ones, are more difficult to sorb. On the other hand, realize another thing. The advantage of having porous, a pill that is porous, is that the pores are charged. And so we can play around with this also. So the pores inside of a cationic pill are typically positive. And so here you can see that it's much easier to extract polar compounds than to extract non-polar compounds, showing that we could really tune our pill porous material to extract certain compounds. Okay, so here I made a comparison between the dense and the porous for solid phase microextraction. And we took advantage of all this knowledge to try to prepare membranes for gas separation. And that's what I'm going to show you next. So I'm going to show you, hopefully I can show you that when we advance in one field, the knowledge can be translated to another field, and that other field can profit from it. Okay, I don't think that I have to talk to you about the advantages of having membranes instead of having absorption, gas absorption, for example, for CO2. In terms of energy intensive, we know that membranes win for sure. However, we also know that the complete separation is very difficult. And so we require a pretreatment if we want to use membranes. In our group, we have been developing materials to prepare CO2 separation membranes. And what I'm going to show you is a result of a PhD work. So here also, we went from dense, non-porous membranes into, we would like to go porous, but if we go to porous, then we really gain flux, but we lose selectivity. And so what we would rather have, it's an asymmetric membrane where the dense layer, it's very thin, and then we have a porous layer that supports the thin layer. In this way, we can have a high flux with a small membrane area and as an efficient system footprint. So let's see if we are on the right track. So the work that I'm going to show now is the work of Andrea Gouveia, which is a PhD student. And this is part of the work that she has been doing. So she has been working on the separation of biohydrogen. This work is work that is supported on previous work from other students. And so she uses the best polymeric ionic liquids that we were able to prepare and dopes them with 40% or 60% of ionic liquid so that we have a better flux and that we have the plasticizing effect on the polymeric ionic liquid that we need. So Andrea prepared PLL composite membranes, dense composite membranes. And so the novelty here was to check how mixture of gases would behave in comparison of pure gases. This work was done in collaboration with the University of Santander in Spain, with the group of Immaculada Ortiz and Daniel Gorri. So this is the typical composition of biohydrogen. And here we did our experiments at temperatures between 20 and 80 and the feed pressure between 1 and 4 bar. The first thing that we can see here for the permeation of gases is that the permeation is much lower in mixed gases than it is in single gases, especially due to the competitive sorption effect, since this is a dense membrane. And this can be observed either for CO2 and also for hydrogen. However, in terms of selectivity, the selectivity is kept when we work with mixed gases. And so these are very good news. Let's see now the performance of these membranes. So this is the Robson plot that tells us the efficiency of my membranes. Here it plots the selectivity versus the permeability of the most permeable gas. The upper bound is the current state of the art, and so we want to surpass the upper bound to surpass the current state of the art. So here are the membranes that we did. Again, 40% of ionic liquid is less permeable than 60%, I don't have this 60%, so 40% of ionic liquid is less efficient than 60% of ionic liquid. In terms of efficiency, this is a little bit smaller, but it has a much smaller permeability, a CO2 permeability. Realize also that when I change temperature, so difference in temperature greatly reduces the efficiency of the membrane in terms of selectivity and also in terms of permeation. And this happens for all membranes. And in what concerns pressure, pressure does not have much effect on the permeation properties of these membranes. So this is a good news. Okay, so what we've seen here is that here we use a dense membrane, and this really illustrates the problem that these membranes have, which is the flux, the permeation, the CO2 permeation is quite low. And so we tried to prepare asymmetric filial membranes, and this is still ongoing work. So Andrea has been working desperately on this in the lab so that she can finish. And so instead of having a dense film, we are trying to create a dense top layer and porous to support the dense layer. So we use exactly the same polymers. And what we do, the first is exactly the same. So we have a casting solution. We use a Dr. Blade's knife and we cast our membrane. And then we just wait for a certain period of time for it to start to evaporate a little bit of solvent on top and to start to solidify or gellify. And then we put our membrane inside of a phase inversion bath, a coagulation bath with a non-solvent until for a very long period of time, typically overnight. Then we take the membrane out and we dry the membrane. So what we are aiming to do is we have the initial casting solution here, and we have this polymer solvent, non-solvent equilibria. This is how we're trying to promote porosity. And we determine the initial casting solution, this critical solution, through viscosity measurements. And then when we put our membrane in the bath, the concentration starts changing and we see it starting to become a little bit jelly, then to precipitate. And as the solvent is being exchanged by the non-solvent, we can see the membrane forming until next morning when we take the membrane out of the coagulation bath. So the key here is to choose the non-solvent, since is to choose the solvent, because the non-solvent typically is water. So what we want is to have very low miscibility between the non-solvent and the solvent. If we have a very low miscibility, we will have a slow exchange of the solvent for the non-solvent, and we end up in a sponge-like morphology. Otherwise, if we have a high miscibility with non-solvent and solvent, we have a fast exchange and we'll get finger-like morphology. And I'm going to show you why this is a problem. So we have a couple of parameters to optimize: the critical concentration, the solvent mixture, casting time, coagulation time, and coagulation temperature. Let's take a look. So these are the ternary phase ternary diagrams that we have been plotting. Here is our binodal curves for two solvents. We did this for two solvents. This is for solvent 1 and this is for solvent 2. So solvent 1, we have different compositions. They are both mixtures of solvents, and we can see that they are different. Of course, that what we want is to have as high as possible two-phase region. And here it's, again, a ternary diagram, but this time for 20, 40, and 60% of ionic liquid. And we can see that all the phase diagrams become very close to each other. So when we put this membrane inside of the coagulation bath, we will have exactly this trajectory through inside the two-phase region. So using solvent 1, we did 5 minutes of solvent casting, and then we just put our membrane inside of the coagulation bath that is water. We can see here that the top layer is dense, and we can see in this cut that we have finger-like morphology. This is after 10 minutes. This is after 20 minutes in the casting solution, and this is after 40 minutes, where the solvent starts to evaporate a lot and we start to have a very smooth surface. Let's take a look at the membranes. The membranes that we have been obtaining are quite nice, as you can see. They looked very flexible, but when we put them in the apparatus, what happens is this. So they are in fact very fragile. So right now we are trying to solve this problem. What happens with solvent 2? With solvent 2, it's quite different. So you see here, after 5 minutes of evaporation, we have the top layer is porous and the morphology is sponge-like. And if we leave it for 10 minutes, we continue the same situation, and for 40 the same, but now the pores are becoming smaller, and here the pores are much smaller. And we still maintain the sponge-like morphology inside of the membrane. Here the pores go from 500 nanometers to 1.6 micron. So let's take a look at the membranes. These membranes look quite nice, and we were able to measure them. And here I have a comparison for you of the results that we get from the dense membranes and the results that we got from these last membranes with solvent 2. So here you can see that they are porous. So I have the permeances here, and the separation efficiency is here. So here we measure the separation efficiency of CO2 and 2. So you can see that by playing around with asymmetric membranes, this is more than asymmetric membranes, it's already porous membranes, we greatly increase the flux for both gases, greatly increase the flux, and we also compromised a lot the selectivity, okay? Then we try to adjust a little bit more this solvent by playing with the quantities of the two components of the solvent. And here we can see that we don't know yet if we have a porous membrane because we did not take it to the SEM, or if we have an asymmetric membrane. We greatly decrease the flux, and the selectivity is again coming up. In fact, here, the permeance, I'm sorry, is really coming up again, and it's much higher than these of the dense membranes. So these membranes here, we still don't know if they are porous or if they are asymmetric as we wanted. Okay. So my conclusions. Oops. So my conclusions. So I hope that I could show you that the creations of pores in dense materials yielding high surface area is a very versatile strategy that can be used not only in analytic applications, but also to the fabrication of thin films for to be used in membranes. In the SPME, all the tests that we've done reveal that these fibers with pores are much more efficient than those that are dense fibers. On the other hand, we can also selectively extract polar compounds due to the porosity, the charge of the pores, the porosity being charged. On the other hand, when we try to separate CO2 for H2 and CO2 and N2, as I showed in the last slide, I show you that we can also greatly increase the permeance of the gases in these membranes. And it's really a matter of being patient and try to refine the conditions of the membrane casting and of the porous forming. And I'm sure that we will be able to come up with asymmetric membranes, or who knows, porous membranes where we can have an increased selectivity. So I would like to thank all my collaborators, my group, and those collaborators that are not here. And I would like to thank you all for your attention. Thank you very much. I'm sorry that I overpassed the time.
No, it's okay. Thank you very much, Professor Isabel Marrucho, for this wonderful, nice presentation. Now we have a room for questions. You can write down your question in the chat so we can read it for you, or you can raise your hand and you can directly ask Professor Marrucho. So questions. Chat.
Comments?
There is LC one.
There's a question on the chat. It's from Nora. I can't read the name, but it says, "May I know what type of solvent did you use to dissolve PIL? PIL?"
What solvent, where, when. So when I have dense membranes, I showed you results from, I showed you when I have dense membranes, it depends if I have the NTF2 anion or the cyanoanion. They have different solvents. Typically we use acetone or we use DMF. Those are the solvents that we typically use. When we go to the porous, we really need to start playing a little bit more with the properties of the solvent. And so we have a mixture of solvents.
Professor Richard Noble.
Yes, hi, Isabel. First, good luck with making the asymmetric membrane. I mean, if you can do
I'm almost there.
No, I mean, I tried it several years ago, actually with the people in Toulouse, and we sort of made something, but it really didn't work. The question I have is that hydrogen is really insoluble in ionic liquids typically. And so I'm surprised that there would be a competitive sorption effect for CO2 hydrogen, because CO2 is really soluble compared to, say nitrogen. And hydrogen is pretty insoluble. So it's just curiosity for me to see that if you make a mixture that you would, that the hydrogen would have some effect on the CO2.
Yes, we were surprised too, but realize that the mixture also has nitrogen, which does not help also because nitrogen is not very soluble also.
Right.
But it is a ternary mixture, but somehow the permeability just greatly dropped. And so I can't see any other thing besides the competitive effect.
Yeah, okay.
Between the gases, because it competition for the sorption. I did not show here the sorption properties, the sorption and diffusion, but that's what it indicates.
Yeah. All right, again, great to see you. Thanks.
Good to see you.
Thank you, Professor. Dr. Byrne?
Okay.
Yeah, hello, Isabel. How are you?
Hi, Byrne. Nice to see you.
Yeah, you have shown a critical point in the ternary system. Is this an estimated critical point, or have you determined this critical point experimentally?
I determined it experimentally. So the data that we have is data. So we determined it experimentally. Yes, the curves. Because I know that so these asymmetric membranes are typically done using this process, and when it's not in polymeric ionic liquids, that People use, for instance, Hansen parameters to estimate the solubilities. But Hansen parameters still do not work for ionic liquids or polymeric ionic liquids. So this is data.
Thank you.
Welcome.
Dr. Margarita asked, why using silica and not other support?
Hi, Margarita. When are you mentioning that I use silica? I used
Hi, I don't know if you're hearing me. I'm just, it was on the first slides that you mentioned the work that you did when using silica coated with the pill. Because I know there are a lot of other materials like monoliths, whatever, that are plenty other supports materials. I don't know why choosing silica. Maybe it was easier to manipulate. I don't know what's the.
No, that was just an example. We always used stainless steel wire.
And why is that? It's easier to manipulate,
yes, because it does not break. So it's much easier to play around with it. Because first we start using silica and it was a nightmare because it would break very much. And so we decided
migrate to the stainless steel.
This is what we use throughout this work.
So basically, the first tests was using silicon, then you migrate to stainless steel because it's harder to break. It's more resistant.
Yes, more resistant, much more resistance. Yes, it's a great improvement. If you want to play around with it, the silica is very fragile. You really have to be careful.
Makes sense. Thank you, Professor.
Welcome.
So any other question? Well, I have a question. Well, my computer it's a little bit slow, but in the case of the microextractions, what what level you have of enrichment factor of the molecules you're extracting?
I'm sorry, I think that my computer is bad also. Can you repeat the question? I could not hear.
Yes. Well, in the microextractions, you showed the chromatograph areas or peaks, but what kind of enrichment factors you obtained for the molecules you are extracting?
So what we were trying to see, it was if we could extract, like for instance, in this one, it was if we could, how much could we extract? So these are not enrichment factors because this was we extract to our material and we desorbed it in the gas chromatograph. So we have higher areas, which means that we can absorb a higher amount of compound than the other fibers. Like the porous here can absorb a higher amount of compound than the non-porous. And that is really important, especially when you're talking about very small concentrations. So to be able to sorb, to specifically sorb compounds is very important because it allows you to go down in concentration.
Yeah, okay.
I don't know if this is what you were asking.
Yeah, because Sometimes you have to deal with molecules in water samples that are present in very small concentrations. And sometimes you want to use um, equipment with low resolution to avoid buying equipment with high resolution to measure the concentration of these molecules. So that's why I was asking.
Okay, but realize here that I'm only sampling the gas phase, the headspace. So I did not use this in solution.
Okay. There is another question from Leila, sorry.
Yes, that's me. Can you hear me?
Yes.
Yes.
Hi. Thank you for a wonderful
Yes.
presentation, Professor Marrucho. So I was wondering if you could. I work with the gas separations, and I was wondering if you could comment a little
Yes.
bit on different types of gas separations. So, for example, if you're separating gases that have similar sizes, like CO2, CH4 maybe, or maybe another gas separation, a very tricky one that also Professor Ortiz worked a lot, like ethane and ethylene. In terms of the membranes that you make, could you make a comment on that, on how you can try to control the formation of the membranes and try to optimize for these separations?
Well, I think that it will be very difficult, if not impossible, to have pores that can, in a polymeric membrane, that can separate between gases. No? Gases have almost all the same size, and with this technique, the solvent, non-solvent technique, I don't think that we'll be able to get pores that can be specific enough for me to separate, or for us to separate between gases. I think that we can leverage some extraction mechanisms like Knudsen diffusion that can be beneficial in the extraction of the compound that has a higher affinity for the membrane. So I think that we should think about the pores as an enhanced surface area and not as a molecular sieving mechanism, because that I don't think that we are ever going to get in these membranes.
Thank you very much.
Hello?
Okay, thank you very much.
Yeah.
I don't know if there is another question, one last question. Well, if we don't have more question, well, I would like to say thank you very much, Professor Isabel Marrucho, again for this very nice talk. It was a very wonderful presentation, right? I would like you to say some last word to the email community.
The last, I think that the email community is very, how shall I say, is very focused on the liquid state. Materials have been playing a very important role in ionic liquids. And I think that it is very interesting also to see that we can tune the material's properties using ionic liquids. So this is a challenge that I think it's worthwhile pursuing. And for the email community, keep up, do not give up, stay together.
Very good message. Okay, thank you very much again, Professor Isabel, for this presentation and for the opportunity to see your presentation. And thank you very much, the audience, for attending today this webinar. Next week, we will have another webinar for you at the same time. I hope to see you again next week. Bye. Thank you very much.
Bye, everyone.
Thank you. Bye-bye.